Okay, is that better? I always forget that one setting that I have to change. Can anybody hear me now? All right, good. Thank you for letting me know. Um, I always forget that one. So, what I was saying, I was saying hello to everybody. So, hey, Alyssa, Daisy, Renette, Lene, thank you for joining us. Anybody else who might be out there who's not in the chat, thank you for joining us as well. So, I was saying that we're going to start with a balancing equation to kind of review from last time, but we're going to do it with words instead of with chemical symbols, because you should be able to do that as well. So sometimes our descriptions of our reactions are going to be more like a sentence. So something like aluminum chloride reacts with sodium hydroxide to form aluminum hydroxide and sodium chloride. All right, so that's another way of describing a chemical reaction. And let's say we want an equation for this. We can write that down. So the way we do that is by going back a couple chapters to our naming compounds work and figuring out how we name these compounds and then what the words tell us about which goes on which side. So I've got aluminum chloride reacting with sodium hydroxide. So that reacts with, that's our clue that those are the reactants. So reacts with tells us this and this are our reactants. And then our other clue is to form aluminum hydroxide and sodium chloride. So that tells us that these things are going to be the products. Now, sometimes they could be written in the reverse of that. So some other words, so it could say something like aluminum hydroxide and sodium chloride are formed via the reaction of aluminum chloride and sodium hydroxide. So same idea, they're flipped, but we're talking about the same process. So you can read it, you can think about what's happening, what are we starting with, what are we ending with, and then we can write from there. So we've got aluminum chloride. So aluminum's plus 3, chloride's minus 1. So aluminum chloride is AlCl3. We're not told the state here, like solid, liquid, gas, aqueous. So I'm just going to leave it alone for now. If it said something like solid aluminum chloride or liquid aluminum chloride, then we would add that state there. So we're reacting with sodium hydroxide to form aluminum hydroxide and sodium chloride. All right. So those are my formulas. Now, if you didn't just know those formulas off the top of your head, that's totally fine. But what you should be able to do is to get those formulas by figuring them out, by knowing the charges on the ions and then putting them together in that compound. If that's still something that you're having trouble with, that you're needing a little bit more practice with, please do that practice now, because this will continue to be an issue as we talk about these things going on in the semester. So don't just say, okay, I'm glad that chapter is done. That was hard. Make sure you go back and actually catch up on that stuff, because we will be using that. All right, so then the last step is to balance this. Now, in the last class, we talked about some balancing strategies and doing atom inventory. Now that you've had a little practice with that, I want to extend it a little bit and talk about some ways to make this a little bit easier on yourself. So one thing you might notice is that all of these compounds are ionic. They're all made from ions, at least the way that we've talked about ionic compounds. So one way that we can use that to help us is by recognizing that OH here is an ion, it's hydroxide. So when we do our atom inventory, it might make things a little bit easier to say, okay, we've got aluminum ions, we've got or atoms, we've got chlorine, we've got sodium, and then we've got hydroxide ions, rather than oxygen and hydrogen. Now, in this particular example, either way is going to be fine because the OH are always together. But let's say you had hydroxide ions over here and you had like nitrate ions over here. Both of those have oxygen in it. So that could get a little bit tricky. But if you think of them as hydroxide ions and nitrate ions and keep them together, that might be helpful. So we can do the same thing over here. Well, okay, let's finish our inventory here. So we've got one of these, three of these, one of these, one of these. Then over on this side, I've got the same thing, aluminum, chlorine, sodium, and hydroxide. And then I'll have one of those, one of those, one of those, and 3 hydroxides here. Okay, so now I can go about balancing however I like. I can start with chlorine, I can start with hydroxide. Let's start with chlorine here. So I'm going to change this to a 3. That way I can get 3 chlorines. That's also going to give me 3 sodiums. And then I'm going to have to put a 3 over here to balance out those sodiums, which will also balance the hydroxides. And my equation's all balanced. So there's a couple of these on I think they were on the pre-lab actually for this week's lab. So make sure you go through those, even if you didn't get them done before lab, or if you're not sure they were right or something, just take a look at those so that you get some practice there. Did anybody have any trouble with balancing equations that you want to look at? Anything that was tricky or particular equations that you couldn't quite figure out how to get balanced this week? Yeah, anytime you write a chemical equation, like an entire equation, you can assume that you need to write it balanced, I think, from here on out. Yeah, they can be from Mastering Chemistry. What do you got? I don't have it open right now, but if you can tell me the reaction, I can go through it. All right, well, while you're finding that, I did want to look at one other type of reaction, and that's this one here, number 9. I'm just going to rewrite it so we can do our inventory. Oh, great. Jennifer's got it. Gaseous carbon monoxide reacts with hydrogen gas to form methane and liquid water. So let's take a look at that one first. So carbon monoxide is CO, and it tells us that's a gas. That's going to react with hydrogen gas and form gaseous methane and liquid water. All right. One thing that's going to help here, and that may be a concern or maybe an issue. So when there's words describing the chemicals in an equation, if those words are just the compounds that we've named so far, that's not so bad. But something like hydrogen gas, you have to know that that's H2 and not just H. And how do you know that? Well, unfortunately, there's no good trick to that. But we can look at the periodic table, and there's a little section right here by my head for all of the diatomic molecules, so molecules that exist as a 2, as a dimer. So we've got, it actually starts at nitrogen right here. So it goes NOFClBrI, and then you've also got hydrogen over there. So hydrogen, and then nitrogen, oxygen, fluorine, chlorine, bromine, iodine. And for my brain, that works best if I think about the shape. It's like that shape. It's like a, I don't know, Tetris shape or something. If I think about that, that helps me remember that. So when you see something like nitrogen gas or chlorine gas or oxygen or hydrogen in an equation, we need to remember that that's actually a dimer, that it's O2 or H2 or Br2. All right, so now that we've got those, let's see if we can figure out what's going on here. So let's start with our inventory as usual. So we'll say we've got 1 carbon, 1 oxygen, 2 hydrogen. And then over here, 1 carbon, 1 oxygen, 6 hydrogen. Right? I think I'm seeing that okay. All right, so the only thing that needs to change here is the number of hydrogens, since the carbons and oxygens are already in balance. So we put a 3 here, and that should change this to 6. And because that H2 is by itself, it actually doesn't affect any of the other atoms. So putting the 3 here is the only thing that's needed to do that balancing. All right, question number 19 on page 6 of the lab packet. Okay, that's another one. Let me see if I can pull that up here. You know, maybe it's in here. No, that's something that you'll need to know. So you'll need to know those 7 7 elements are always dimers. They're always 2 of them in a chemical reaction. Okay, number 9 on the lab packet is see if I can find it here. What is the name of the product? Is that I must not be looking at the right thing. Yeah, let me look at the periodic table again. So they are hydrogen over there, then nitrogen, oxygen, fluorine, chlorine, bromine, iodine. And if you want to know why that is, you actually do know why that is. Whether you think you do or not, it has to do with the Lewis structures. So those Lewis structures are what they are because they take those 2 elements in there together, or they require that to be stable. So I'm having trouble with the number on the 19. I'm sorry, 19. Okay, that makes more sense. Thank you, Maria. Okay, yeah, this is kind of like what I was like the example we did before, but this is a little bit better one. So let's look at this one together. Sorry, I'm trying to copy it in here. All right, there we go. Yikes, that doesn't look good. Hold on. Okay, close enough. So here's another example of that ionic thing that we were just talking about. So here, yes, it would always work if you do it the way that we did it originally. So we could go CONOPNA and count them all out on each side. But recognizing that there are nitrate ions here and phosphate ions, and that they don't change throughout this reaction. So nitrate stays nitrate, phosphate stays phosphate. That means that we can keep them together in our balancing, and it's going to make things a little bit easier on us. So when I do the inventory on this side, I would say I've got 1 cobalt, 2 nitrate, 3 sodium, and 1 phosphate. Of course, those ions are also charged, but just for the purposes of balancing, that doesn't matter in this case. The reason to do it this way, so if we did this as just oxygen, then we got to count, okay, 6 oxygens here plus 4 here is 10. And then every time we change this, we've got to remember to count that. And it would work, but it introduces a chance of a lot more error, because maybe you forget to multiply by 2 one time, and suddenly everything's thrown off. This way, we've got these 4 species, and we can just think of them as whole things. So on this side, then, I have 3 COs. I have 1 nitrate. I have 1 sodium, and I have 2 phosphates. Yeah. All right. So now we can start balancing. Again, now we can start wherever we want. Normally we would say, oh, there's a lot of oxygen around in this reaction. Let's leave that till the end. But because we group that in with the ions, we can really start anywhere we want. So I will start with cobalt. 1 here, 3 here. So I'm going to want to put a 3 there. And so now I adjust this, and look how nice and easy this is. Now instead of 2 nitrates, I've got 6. So instead of saying, oh, well, I had 10 oxygens, and now I've got 3 times 2, so that's 18 plus 4 is 22, so 22 oxygens. So it's a lot easier if we just group them together and call that nitrate. All right, so now I've got 6 nitrates, so I'm going to want 6 nitrates over here as well. And then that also means I have 6 sodiums now, because I changed that as well. Yeah, if there's something else that's not part of an ion, you can just keep it separate. Yeah. And then the only time I would say, just to be careful, if this doesn't work, when you don't want to keep the ions together, is if the ions don't stay together. So like if this is nitrate on this side, but there's no nitrate on this side, it's like, NO2 or something, or NH3, like there's some other reaction, something else is happening, and the N and the O are breaking apart, then you can't keep that together. But as long as it's on both sides, you can keep it together. All right, so there's my 6 nitrates. So now I've got 6 sodium. So in order to get that over here, I'm going to have to put a 2 right there. That gives me my 6 sodiums and 2 phosphates. And it looks like I'm all balanced up. So that all works. Okay. And then the last one I want to do before we move on, unless there's more questions, is one other thing that comes up that we haven't seen yet. Sure. So let's say we have this molecule, C4H10, which is butane gas, and we want to do a combustion reaction. So we want to react that with oxygen, and those products are carbon dioxide and water. So this is the burning of butane gas and oxygen, just like a lighter would do, or a butane torch. All right, so again, start the same way. Count up our atoms here. So here's one where we don't have any ions, so we're not going to worry about trying to keep anything together. All right. So again, we want to start balancing, and we can start balancing with the carbons, or we can start balancing with the hydrogens, but we definitely want to leave the oxygens till last, because they're in multiple different things. So we don't know what the ratio of these two are yet, and that's going to control how many of these, so we're just going to leave that for now. But what we can do is we can do carbon, let's say. So 4 here and 1 here. Change that to 4. And that's going to affect the oxygen count also. So notice when we change pretty much anything here, it's changing our oxygen count. And so that's why we leave the oxygen to last. Then we want to balance the hydrogens. So 10 to 2, we're going to need a 5 there to make that 10. All right, so carbons are balanced. Oh, sorry, I forgot to adjust my oxygen again. So now the oxygen on this side is going to be 8 plus 5, which is 13. Okay, so carbons in balance, hydrogens in balance, oxygen's not. So we've got 13 on this side. We want 13 on this side. And here's where we run into a problem. We only have O2 on this side. So there's nothing we can put in front here that gets multiplied by 2 and becomes 13, unless we were to use halves, which we don't do. We could say that there are 13 over 2 O2s, but that's not how this is usually done. So we're kind of in a problem here, because we've got nothing that fits. So and this is a common thing that comes up in a lot of equations. So if you get to this point and you're like, oh, I have to put something here, but because I can only change even numbers, I'm stuck. Well, the solution is you need to just double everything so that you get rid of those odd numbers. So what we can do is we can put a 2 here instead of a 1, which is going to change this to 8 and 20. Then we can we'll just ignore oxygen for now because we're going to get to that in a minute. Instead of 4, we'll put 8, and instead of 5, we'll put 10. So we're just doubling those. And the reason for that is the relative ratios are going to stay the same. So we don't have to rebalance everything else because the ratios are the same. So we can change our new inventory serial. You'll notice there's still 8 carbons on each side, and there's still 20 hydrogens on each side, so it's still balanced. But now instead of 13 oxygens, we've got 16 plus 10, which is 26. And that now is an even number. So we can say, okay, what times 2 is 26? Well, it's 13. And now our equation is totally balanced. All right, so when that comes up and you can't balance it by just adjusting one thing, you may need to change other things as well. You may need to double everything or triple everything to get some sort of common number that you can work with. All right, let's look at energy. So you can ignore this part because I switched the order a little bit. I forgot to delete that. We haven't converted any moles of anything yet. Yeah, good question, Jennifer. So yeah, you always want to use the least common denominator. So if you end up doing a bunch of stuff to try to double everything and you end up with these huge numbers, you want to divide them down to the smallest whole numbers that you can get. So if you balance some equation and you've got 4, 4, 4, 8 as your numbers, that should really be 1, 1, 1, 2 if you reduce those down. If it's something that I'm manually grading, I would probably give you a break on that because the ratio is still right. I believe if you're working in mastering chemistry, you do need to make sure to reduce those down. Okay. So we've talked a little bit about energy in terms of how we have, yeah, mastering chemistry is mean. It's not mean, it's just, they want to do things right. They want you to do things right. I also want you to do things right. I'm just, um, if mastering chemistry is being mean to you, just let me know and I will correct it. All right, so we talked a little bit about energy in terms of like one way that we determine chemical changes have occurred. If energy is released or absorbed, that's a good indication that some chemical reaction has happened, that something's getting hotter or getting colder. So in this little bit of this chapter, we're going to look at how we quantify that energy, and we're going to introduce this idea of some different kinds of units, and then how we think about energy in chemical reactions and chemical processes. So two of the main units, there are a lot of units for measuring energy. The ones that we use most commonly are the joule and the calorie. The calorie with a little lowercase c is defined as the amount of energy it takes to raise 1 gram of water 1 degree C. So if you have a gram of water, which is a cubic centimeter of water, so about that much water, or a milliliter of water, and you want to raise it from 25 degrees C to 26 degrees C, that's going to take 1 calorie. And that calorie could also be expressed in a smaller unit called the joule, and that would be 4.184 joules. You don't need to remember that conversion. I would give you that number if you need it, but those are just two common units for measuring energy. Now, confusingly enough, the calorie that we're all used to from our food is not this calorie. It is the capital C calorie, which is known everywhere else in the world as a kilocalorie or a kcal. So that is actually 1,000 of the little c calories. And that can be a little bit confusing. So when you see that your food item has 100 calories in it, that's really 100,000 of these little c calories. So that's enough energy to raise the temperature of a gram of water 100,000 degrees C. In theory, obviously, that's not really going to happen. So then you can look up some of these definitions of different types of energies and think about that. I do want to I guess we can talk about these a little bit right now. So kinetic energy is energy of motion. So when something's moving, it has kinetic energy. Um, the internal energy of something is called its potential energy. And there are some different ways of expressing that. If you've taken physics before, kinetic energy is all about like, a ball being thrown or moving around or something. Potential energy is like something up high because then if it falls down, it releases that energy. There's some good examples also. Um, Thinking about this kind of stuff in the book that's linked. So I've got that here. So this chapter on energy talks a lot about some of these different types of energy. So if you think about something like a waterfall or a dam, the Hoover Dam shown here, you've got a lot of water with a bunch of potential energy because it's up high. And then when it falls, it's converted to kinetic energy. And then if it falls through a dam, it's actually transferring its energy to the electrical generator and becoming electrical energy. So there are some good examples like that in there. Um, Another thing when we talk about energy that directly involves chemistry is thinking about the difference between these ideas of energy, heat, and temperature, which are all sometimes used interchangeably, but they're very different. So temperature is actually proportional to the kinetic energy of the particles that are moving, of the atoms. So temperature is not a measure of heat, and it's not really a measure of energy. It's more about the particles moving. So I'm actually going to change this. It's not quite how fast the particles are moving, but it's more like it's proportional to the kinetic energy of the particles. So um, if you're talking about the same type of particle, so the same kind of atom, the same kind of matter, if it's moving faster, it has more kinetic energy and therefore a higher temperature, and slower, it's not. So um, when we talk about heat, heat is a transfer of energy or an exchange of energy that is that goes along with a temperature change. So now we're talking about energy again. So heat is actually the transfer of energy from one place to another, or from some particles to others. The other way you can transfer energy is something called work. So when you're like pushing something or moving something, that's transferring energy via work. But in chemistry, we're going to focus more on the transfer via heat. And so when we talk about heat coming in to a system, that's called an endothermic reaction. And we talk about heat given off, exiting, that's called an exothermic reaction. All right. One thing that's a little bit confusing about this is an endothermic reaction feels cold because the surroundings, you are transferring energy into the system. The system is absorbing energy. So the level of energy of the system is going up, but it feels cold because it has to suck that energy from the surroundings. And then the converse of that, an exothermic reaction, the actual chemicals themselves are going from a high energy state to a lower energy state, releasing all that extra energy out, and that makes the surroundings feel hot. So that makes us, if you touch it, if something feels hot, that is an exothermic process. So let's take a look at this, not in a reaction first, but just in phase changes. That's what these graphs show. So let's look at a heating curve for water. So a heating curve is graphing what is the temperature versus how much heat is being put into the system. So we're starting with ice, right? Solid ice. And you can warm up solid ice until you get to what we call the melting point. And at the melting point now, the ice is we know it's 0 degrees C. And now we put in more energy and we melt the ice. So melting is an endothermic process because you have to put heat in to get it to happen. Then you can heat up liquid water from 0 degrees C to 100 degrees C until you get to the boiling point, and then you need to put more energy in to boil that water and have it become a gas. And I think we'll talk about this a little bit more in a couple chapters as well. And then the reverse of that is the exothermic processes, condensation and freezing. So condensation is exothermic, and that's one reason that steam burns are so dangerous. That when steam hits your skin, all of that condensation energy, all that energy that it takes to actually break apart water molecules from the liquid to the gas state, all of that is being transferred exothermically into your skin. And so that's a lot more energy than just touching something hot. So steam at 100 degrees will give you a worse burn than water at 100 degrees, even though they're both at the same temperature, because of transferring that energy from the phase change, that exothermic process. The other thing that's a little bit sometimes counterintuitive here, freezing is also an exothermic process. We think of it happening at cold temperatures. Freezing happens in your freezer. But one of the reasons freezing a freezer takes a lot of energy is because that freezing process actually gives off heat. It gives off heat when water freezes. So the freezer has to absorb that and continue to cool down and remove heat from that system to keep that frozen. Okay. So going now to a chemical reaction, one thing about energy transfer is it's somewhat arbitrary how we define it. So we take these two parts of our whatever we're looking at, the system and the surrounding. And the system is the thing that we're focused on, and the surroundings is everything else. But that's arbitrary. We can define the system however we want. So if we're talking about let's for example, let's talk about cooling your skin by sweating. As you may know, when you sweat, you've probably heard that is helping cool you off. Well, why is that? Well, that's because evaporation is an endothermic process. So you are absorbing energy. So the sweat is absorbing energy from your skin in order to evaporate, to become a vapor. Now that assumes that the system is the sweat, is the actual liquid, right? It's the one absorbing the energy. If instead we talked about the skin being the system, well, then it's more of an exothermic process because the skin is giving off its heat. So depending on what you're thinking, what your system is, you have to think about, is energy going in or is energy coming out? Now, to make this a little bit easier, in chemistry, the system is pretty much always the molecules. So the individual, whatever the chemicals are that are doing those things, that's the system. And the surroundings is everything else. It's the solvent, it's the glassware, it's the air, it's whatever else is involved in the system. So when we look at transfer of energy in a chemical reaction, then that's what we're always talking about. So these diagrams here are called reaction coordinate diagrams, and they are a graph of what's happening with energy change in a chemical reaction. So in an endothermic reaction, the reactants start at a lower energy and the products end at a higher energy. So this difference with this green arrow here is the heat that's absorbed during the reaction. And we're going to talk about the hump in a second. In an exothermic reaction, the reactants start at a higher energy than the products. And so as the reaction is done, heat actually comes out. So heat is given off or evolved during the reaction. And that's what we call an exothermic reaction. Now for both of these, there's this hump that's known as the activation energy, or the energy of activation. And that's because for these reactions, they actually require energy to be put in first. So think about something like burning, like combustion of gas or any kind of oil. That stuff can sit in the earth for millions of years, right? It can sit in a gas can in your shed for forever. Nothing happens to it at all until it gets a spark. And then all of a sudden, it has the spark and it can combust, it can explode. So that spark is the activation energy. It's energy that needs to be put in just to get this thing going. And then in a exothermic reaction, because energy is being given off, the energy that's given off kind of acts as the activation energy for more. In an endothermic reaction, it's a little more complicated because there's some other stuff going on that's driving that reaction. So as you're going through this, think about these questions and really think about what, how you're defining these things and how you're deciding if energy is going in or going out. We're not doing the calculations that are often associated with these things. We're focusing on the definitions and on thinking about what's happening. All right. So the last part here is talking about the rates. So how fast a reaction goes. And that is different from how exothermic it is. So we think often like an explosion is really fast, but that's actually different. An explosion is it's very exothermic. It's giving off a lot of heat. It's giving off a lot of energy, but it's not necessarily fast. Fast has to do with how much activation energy is necessary. If it's a low amount of activation energy, it's fast. If it's a greater amount, it's a little bit slower. But there are ways we can control that. So there's this example with a coupon here. But the more chemically important way of doing that is with something called a catalyst. You've probably heard that term before, but the catalyst decreases the energy of activation by providing a different mechanism through which the reaction can proceed. And in doing so, increases the rate of a reaction. So, for example, many biological processes would not happen spontaneously or would require a huge amount of energy. You'd have to be burning up inside your body to actually get that process to work. But instead, we have these things called enzymes, which act as catalysts to do those processes at a lower with a lower energy of activation. So they become faster then. And then there are some other things that affect the rate of the reaction that you can read about, including the concentration of the reactants. So the greater concentration, the faster the reaction goes. The surface area of, if you're talking about solid reactants, the greater surface area means faster reaction. So if you want a faster reaction, you got to really grind everything up really small. Temperature, remember what we said about temperature a little while ago, it's proportional to the speed of the molecules. So if the molecules are at a higher temperature, they're bashing into each other more, they're going to react faster. And then finally, the catalyst that we just talked about that can change the activation energy that way. So any questions about rates and that kind of stuff? There's just one little thing left to look at, but I'll pause for a second in case you have other questions. All right. So the last thing to talk about here is called equilibrium. When we looked at chemical reactions and the chemical reactions we drew yesterday and today, we always used this forward arrow, so a left to right arrow. But in reality, I don't know why there's a little black speck on my screen there. But in reality, reactions actually always are proceeding both ways. They're going forwards and they're going backwards. So in this case, you've got a forward reaction, a reverse reaction, and then written as a single reaction, you're going back and forth. Now that's a little bit of a typographical mistake here. The more correct way to express that is two arrows on top of each other like that, and that's what you'll usually see for a reaction that goes back and forth. And in fact, all reactions really go back and forth. It's just a matter of to what degree do they do that. So some reactions proceed very, very much in the forward direction, other reactions very much in the backward direction, and some kind of balance out right in the middle. But once those two directions, whatever they are, whenever those rates balance out, then we call that chemical equilibrium. So in a process like this, you're starting with all starting material, but you're not actually going to get to all products. You're going to get somewhere in the middle where you've got some stuff going forward, some stuff going backward. So there's all this kind of like this balance. So what do you do if you want to do a reaction and you want it to go all the way to completion? But naturally, these chemicals don't go in one direction, they go back and forth. And you can control that with something that's called Chatelier's principle, which just says that if you put a stress on one side of the equilibrium, you can push it the other direction. So, for example, if you add more reactant, you now have more reactants on the reactant side than what would be balanced, and so that's going to push the equilibrium a little bit more and give you some more products. But you can do the same thing by actually removing the product. So let's say you have some sort of tool where you can remove all of the SO3. Well, once again, it's no longer balanced, and so now the reactants are going to react a little bit more to give you some more SO3. So a common technique, experimental technique, when you have this equilibrium is to pull out the reactants as they're formed, which forces pull out the products as they're formed, which forces the reactants to then make more of that. Right? And so there's some examples here about what would happen, how would the reaction change, how would it move to reestablish that equilibrium after you do something to it, after you add something or remove something. And you can think of it very simply as things like, like a couple big buckets connected by a tube. If you take some water out of, if you dump a bunch of water in one side, it's going to balance out. But then if you take water out of one side, it's going to push more over to that side. If you put more water in one side, it's going to push more to the other side. So it works just like that, and we can use that to help control what's going on with our equilibrium reaction. All right, so questions about chemical reactions? I removed the password from exam 1, so you should be able to go in there and check your exam and like go through the questions that you what you did. If you think that you got stuff marked wrong that should actually be right, just let me know or screenshot it or something and send it to me. I've gotten a few requests from that, so I'm still kind of working through them. And then next week we will work on, we'll get into some math and do some unit conversions and moles. So something to look forward to there. And I will see, I'll hopefully see you online on Tuesday. So let me know if anything else comes up. And otherwise, yeah, I'll see you then. Good night, everybody. Thanks.